Welcome back, everybody. This is lecture 2 on integration by parts and the tabular method. So in the last video, I introduced what integration by parts is, and in this video, I'm going to show you the tabular method, which is a very efficient process for doing integration by part problems. It really streamlines the whole process, and it organizes all of your calculations in a nice chart. So I've just kind of summarized what the tabular method is right here. So it efficiently performs integration by parts, and we're going to organize all of the differentiation and integration steps along the way. So I'm just going to show you many integration by parts examples in this video, and I'm going to get you comfortable using the tabular method. So that's my goal. Let's start with this problem right here. So it's going to be the integral of x squared cosine of x dx. So the thing you want to notice about this is that you have two very different types of functions being multiplied together. Remember, they're from two different kind of families. This right here is some kind of algebraic object. It's a polynomial. And then this right here, the second thing, is a trig function. So you have two very different looking things, and U substitution is not really going to help us with this problem. So that's your indicator that this is an integration by parts problem, because you have two very different looking things. Over here, I was nice enough to give us kind of the summary of how to choose U. So I have the mnemonic here, liate, for logarithms and inverse trig functions are chosen first. Then algebraic objects are chosen next. Then trig functions, and then finally the last thing you would choose are exponential functions. So if I look over here, I do not have any logarithms or inverse trig functions. However, I do have an algebraic thing. I have x squared. So because it's the first one on this list, that's going to be my choice for U. So what I'm going to say is I'm going to have U be x squared. So this chart is kind of the whole point of the tabular method. This is like where all of your work happens. So U is going to go here. And remember, dv is just the other stuff you didn't pick. So the other stuff I didn't pick is right here. It's this cosine x dx. And what you need to remember for the process here is that in the left column, we're going to differentiate going down. And then in the right column, we're going to integrate going down. And you have to keep these two things separate. You can't mix them together, otherwise this could become a mess. So the polynomial thing I've chosen is a great choice, because when I differentiate this a couple times, like for example, I go to 2x and then 2 and 0, if you choose a polynomial to start with for U, this will go to 0. And you're going to see in a second why that is very useful for this method. So here, we need to integrate. Over and over again, I'm going to give myself just enough to catch up to this 0 entry. So the integral of cosine is sine. And if I go again, the integral of sine is negative cosine. And I need to go one more time. You're going to see why. So the integral of negative cosine is negative sine. So I've stopped here because I've reached a row here that's 0. You're not always going to have a row that has 0, but in this case, I'm going to stop here because I do see a 0. Now, from this chart, we can actually write your final answer. So this is what you do. Starting with the first row, you're going to have a plus symbol. Then you're going to have a minus symbol, and you're just going to keep alternating each row. And I do this just to remind myself of which row I'm on. And then once you have these, you multiply the diagonals together. So the first diagonal is this right here, and it's a positive to start with. So I have positive x squared times sine x. And the wonderful thing about this is what I'm doing is I'm writing the final answer. Like, I'm already there. I just have to write it all out. The next one, here's an example where you have to be very careful. So here I have a negative sign to start with for row 2. However, in the diagonal itself, I have a negative sign as well. So a negative and a negative are going to cancel. And I'm just going to get 2x cosine x. So that's my second term. I'm going to go down to my third diagonal here. It switches to a plus now. And I have 2 times negative sine x. So overall, that's going to be a negative. It's going to be negative 2 sine x. And then notice after that, I've run out of things to write because they would just be zeros if I keep taking the derivative. So all these diagonals will go to 0. And then I need to remember my plus c because it's an indefinite integral. But this right here is actually the answer to the problem. So you can see how this organizes everything so nicely for you as you're doing this. There's a couple other situations that you're going to get into that you need to recognize what's going on in the table. But once you've seen enough problems, this will be the fastest way to do most of your integration by parts problems, and it's the preferred way that I do them. So I hope that's good. I'm going to go ahead and move on to the next problem now. So this one's going to be the integral of ln of x over x cubed dx. So taking a look at this, I could rewrite this if I wanted to as ln of x times 1 over x cubed dx. And now I need to make my choice for u. So ln of x, that's my very first choice on the list, a logarithm. So I'm going to make u ln of x for sure. That is the first thing I'm supposed to choose in this list. And then for dv, it's going to be this. It's going to be 1 over x cubed dx. And remember, I'm differentiating in the left column, and I'm integrating in the right column. So then the derivative of ln of x is 1 over x. And then the antiderivative of 1 over x cubed is going to be x to the negative 2, and then times negative 1/2. So if you checked your work, you bring the negative 2 in front, it cancels, and you have the negative 3 here. So notice in this case, if I kept differentiating, this would never go to 0. You would just keep getting greater and greater negative powers of x. So here's another situation that you want to be on the lookout for when you're doing these. If you notice that in this horizontal space right here, if you multiply those two together, if you can integrate that function, you should just stop. Because what am I actually looking at right here? If I can use a different color, this is my choice of u, which is ln of x. This is my dv. And then here I have du, and I have v. So what this second row gives me is the v du integral from the integration by parts formula. So let me write out what this is going to look like. So let me section this off. So here I'm going to write the integral of ln of x over x to the third dx is, so my first row is plus, my second row is minus. If you multiply the first diagonal here together, you're going to get negative 1/2. And then I have x to the negative 2. And then I have this ln of x right here. So this was u times v. I have this times this. And then I'm not going to do another diagonal here because I don't have one. I'm actually going to multiply. I'm going to multiply the final row that I can integrate now. So there's a minus sign here, and there's a minus sign here. So I'm going to get plus the integral, because this is a v du, a row is a v du. So I'm going to get plus when these minus signs cancel. And I have 1/2. And then here I have x to the negative 1 and x to the negative 2. So that's 1 over x cubed dx. So the original integral is equal to this diagonal plus, plus these multiplied together. The thing is, you recognize this as being the integration by parts formula. So all I did here was, this is u times v minus v du. That's all we did for that. OK, the point is, this row right here is much easier to integrate. So my final answer is going to be negative 1 over 2x squared ln of x. And if I integrate the 1 over x cubed, I just did that in the previous step. That was negative 1 over 2x squared. So this gives me negative ln of x over 2x squared minus 1 over 4x squared. And then don't forget your plus c at the very end. That is a c, trust me. OK, So that's another situation that can happen is you don't need to do all of these diagonals. Like in this case, you could stop when you see you identify a row that you can integrate readily. All right, let's do one more example. So this one is going to be e to the x sine of x dx. And I picked this example on purpose because this is a very special type of integral. This is a circular integration by parts problem. And I'm going to show you why in a second. So first choice is we always have to choose du, or sorry, we have to choose u and dv. So on my list here, I say trig functions is third and exponential functions is fourth. I think you could honestly flip those. It doesn't really matter. But the way I'm going to set this up is to make it as easy as possible. So what I'm going to do is I'm going to say, OK, I'm going to go with the order that's here. So u is going to be sine of x. That's what I'm going to differentiate. The other stuff is going to be dv, which is e to the x dx. And just to give you some insight here, I'm going to integrate e to the x. I think that's much easier than integrating sine x over and over again. So that's why I made that choice. So then if I'm going to differentiate this, I get cosine of x. And if you integrate e to the x, you just keep getting e to the x over and over again. So this never goes away. Neither does this one. Derivative of cosine of x is negative sine x. Derivative of negative sine x is going to be negative cosine x. So neither one of these are going to 0. We're going to have to do something else, and it's actually slightly more nuanced than this one. Well, one thing to notice here is that the integral of e to the x sine of x dx is equal to, we can multiply this first diagonal to get together. Let me write my plus and minus symbols here. So I've got them all written out. My first diagonal is equal to e to the x sine of x. My second diagonal here is minus, because the minus in front, e to the x cosine of x. And then notice, if I were to just stick to this horizontal row, this is the integral I started with. So that's the insight here. So now I'm going to write out what this horizontal line is. This is going to be, overall, I have a minus integral of e to the x sine of x. So that's what happens when I have a horizontal row. I leave it as an integral. Diagonals are not an integral. So then what do I do here is I notice the left side of the equation has a like term over here on the right side. So I'm going to add this to the other side. I'm going to add this integral to this integral. Now I have two of them. So add this to the left side. I get two of these integrals that I'm looking for is equal to, and then the right side now, if I've added this, is going to be e to the x sine of x minus cosine of x. And then finally, to get the answer, you just divide both sides by 2. So what I wanted was this. Divide both sides by 2. Just allow me to do this. I'm going to write over 2, over 2. And then that's my final answer right there. Oh, plus c, right? Plus c. OK, so these were 3 very different looking examples, but I used tabular method for all of them. In the next part of this video, I'm just going to have you practice a couple more problems with tabular method. So I'll see you soon. I wish there was an easier way to clean this off. We're going to count this as a workout. This is going to be my workout for the week. This. For the week. Probably the year. 2 years. Welcome back. So to finish up this video, I have 3 more examples where we're going to practice the tabular method. I think it's a good idea, if you are comfortable with the stuff you've seen so far, you should pause the video, try these 3 on your own, see where you get stuck, see if you can finish some of them, and then come back to the video and see how you did. I think the best way to learn math is to do it, first of all, and then secondly, and almost as importantly as just doing the math, is finding where you make the mistakes. you need to go back and edit your work, and you need to find every single spot where a mistake happens. And the more mistakes you can find, the more likely you're not going to make those mistakes again, because they'll be in your mind that you typically make a mistake there. So I encourage you, you have the luxury of having this video in front of you, so pause it, try the problems, unpause it, and see if you can find any mistakes that you're making. Okay, I'm going to go ahead and get started. So I have two very different looking functions. This is an integration by parts problem. It's pretty similar to the other one we did in the first part of this video. I'm going to let u be x squared, because on my list that I still have over here, x squared, this algebraic, comes before the trig function right here. So u is going to be x squared. dv is going to be sine of 10x dx. Remember, you're going to differentiate the left column, and you're going to integrate the right column. So this will be 2x, 2, and 0. If I differentiate this, going backwards here, you have to be pretty careful. The integral of sine is going to be negative cosine of 10x. However, because I'm going backwards, I need to divide by the 10. That's because I'm doing the chain rule in reverse. If I go backwards again, I'm going to get negative sine of 10x. And then another 10 is going to join that 10 in the bottom, and now you're going to get 100. So it's going to be this over 100. If I do one more, if I go backwards, I get cosine of 10x, and now I get divided by 1,000. So that's where I am here. This side went to 0, so I'm just going to write out my final answer. Remember to take these and alternate the signs by row. So I have plus, minus, plus, minus. My first diagonal is going to be negative x squared cosine of 10x over 10. So I multiplied my first diagonal. The second one, I have a negative here, and I have another negative here. So overall, it's going to be plus 2 over 100 is going to give me x over 50. And then I have the sine of 10x. I have one more diagonal to do. I have a plus sign here, plus here. So it's going to be 2 over 1,000, which is 500. I'm going to have plus cosine of 10x over 500. And then don't forget your plus c. So we are just done, because that column on the left went to 0. So I just write out all of the diagonals I have. And then that's my final answer. And now I just kind of double check and make sure we're good. I think we're good. I think that's the answer. This problem is very curious, because you don't have two different functions that are visible here. However, you actually do. So in the order of choosing things, the first choice is logarithm. So ln of x is my choice. What's left? Is there anything left for dv? Dx. There is something left here, and it's dx. And you could say it's 1 dx. I'm going to differentiate on this side and integrate on this side. So if I differentiate ln of x, I get 1 over x. And then if I integrate 1, I get x. And I recognize that this row right here, this horizontal line, I could integrate that if I multiply that together. That's easy enough for me to do. So I'm basically just going to write the integration by parts formula. So here's u times v. This is the main diagonal, x ln of x, minus v du, which is this row I have here. So minus these two multiplied together. That's 1 dx if you multiply these two together. And then this is x ln of x. And if I integrate 1, I get x plus c. So we now have the integral of ln of x. And you may recall that the derivative was 1 over x. So now I can go forwards and backwards with this one. But there's my answer to that. Here's the last one. So we do have two functions I'm working with here. One of them is x to the 1/2 power, and the other one is log of x. Which one of these goes first? Well, log is the first choice on my list here. So I'm going to say u is going to be ln of x. dv is going to be the leftover stuff, which is x to the 1/2 dx. So remember, I'm going to differentiate here, and I'm going to integrate on this row. The derivative of ln of x, I just did it before, is 1 over x. Plus sign, minus sign for each row. The integral of this, I would add 1 to the power, and I would get 3/2. And then I take the new power and flip it, so it would be 2/3. And now from here, I know that this is not going to go to 0 if I keep differentiating. But I'm going to recognize, just like before, this row is something that I feel confident I can integrate on its own. So I'm just going to write out, just like the format for this one, the main diagonal multiplied together is 2/3 x to the 3/2 ln of x. So that's not an integral because it's my diagonal. But this row right here is going to be in an integral. And it's going to be minus, I only see a minus sign, only one of them here, minus. If I multiply this together, I get 2/3 integral of 1 over x times x to the 3/2 is x to the 1/2 dx. I can integrate that because I just did it before. So this is going to be 2/3 x to the 3/2 ln x minus 2/3. And the integral of x to the 1/2, I did it right here. It was 2/3 x to the 3/2 plus c. And if I want to write my complete answer, it's going to be 2/3 x to the 3/2 ln x minus 4/9 x to the 3/2 plus c. And there's my final answer. As usual, I nervously check to see if we're good. I think we're good. So how did you do? Did you pause the video? Were you a good student? Did you try these ahead of time? Did you just veg out? Are you not even here? Are you not watching my video? I hope you're here. Thank you for being here. I will see you next time for lecture 3. And let me know if you have any questions. You can send me an email at jstressy@ufl.edu. So have a nice day. Bye.